Thank you very much for having the opportunity to have this presentation here. Well, when we are looking for the African humid period in the Holocene, then we have to know that the desiccation of the Sahara was one of the most famous changes in ecological pattern in the world, I would say, in the Holocene. And this desiccation took place. It depends on where you are, between 7 and 3,000 years before today. And we can observe an early onset at the northern Saharan margin, but in generally we have got a problem that due to this desiccation, entire Holocene records of climate or even paleoecology are very rare from this region because the archives are not present. So when you look for the current scientific debate about the aridification of the Sahara, we have got somewhat controversial views about this desiccation. So I plot here two very prominent records from the Saharan desiccation. One is from the eastern Sahara, one is from the more western part. And while the discussion is about does there exist a more gradual transition to aridity towards the late Holocene, or was it more an abrupt transition, as mentioned here by the Dimenocal group, around 5.5, I think, or 5.3. So, looking to our own record, which is in the Middle Atlas of Morocco at the North Saharan desert margin, we recovered in a karstic lake, and the name is Sidi Ali. We recovered a 20 meters long core, which was already investigated by pollen dating, which was done by my colleague William Fletcher, which is also present here at the meeting. And well, it is a mountainous lake, and we currently publish in Quaternary Science Reviews a first proxy or multi-proxy record from this lake, and one of the major curves of this record is a stable isotope record, and you can see here, following our interpretation, strong decreases in winter rain in the early Holocene, which are more or less paced by millennial phases. Yeah. So there are some prominent ones like 8.2 or also 10.3, which you know maybe also from the Bond record. So we have got from the hydroclimate, we have got here a strong Atlantic signal in the record, and we want now come to this presentation and to the dust record. I want to show you here the Holocene variability of Saharan dust in this record, and we want to see if there are existing synchronicities between the Saharan dust supply and the North Atlantic hydroclimate, which I've shown you before. So there's a question, do these arid phases in the northern Saharan desert margin, do they coincide with Saharan aridity? So this is a compilation from a modern dust model, which is done by my colleague Hans von Suche-Dolitz, which shows you the current conditions here at Sidi Ali. So we have got a maxima in dust supply in summer, and the origin of the dust is coming from south and the south west during summer. This is also a view, a supra-regional scale by satellite data, which is done by my colleague Kerstin Schepansky. So you can see that the major dust production areas in the Sahara, that they are sub-Saharan. And here in the yellow bars, they show you the major dust trajectories during summer, going to the north. And and you see the position of Lake Sidi Ali, and our idea is now that the dust which we will record might be even from the southern origin, and maybe probably also from the sub-Saharan. So what we do is we did a transect, a terrestrial transect. You see in the blue cycle. Is there? No, it's not possible. Okay, but you see the blue cycle. This is Lake Sidi Ali. And we have got volcanoes in the north of Sidi Ali, which are absent in the south. And we did a terrestrial transect from surface samples from the north of Sidi Ali towards the high Atlas, towards the pre-Saharan depression, and also in the anti-Atlas forelands. And we want to create a somewhat a provenance transect of siliciclastic materials which are deposited in the lake. So, and then this is only one example. We have too many data and too many ratios, but this is the idea how we works, or I want to give you an idea how we works. You see here on the x-axis, you say the nickel-aluminium ratio, a siliciclastic ratio, and you see the chrome-aluminium ratio on the y-axis. And well, in the middle of this plot, you see the gray circles. These are data from the Sidi Ali record itself, and the other ones are data from the terrestrial samples. And you can see here that for these selected ratios, we might be able to make a reconstruction of the provenances, siliciclastic provenances from the north. These are the volcanoes in the black squares, and the other samples, the grayish and the white squares from the high Atlas in the south. And even when we can go further south, you see here data from the pre-Saharan depression, but also secondary data from the literature. And they show for these two ratios, they show fine separation in or show indications for this southern provenance. In total, we had more than 7 siliciclastic proxies or ratios, and we did we did also grain size analysis. Yeah, I forgot that. Yeah, and what I want to say here is this is done by my colleague Elisabeth Dietze. We have got a very fine silty end member, which we interpret as remote dust, and we've got a third end member, which has also high variance, which is much coarser, and we interpreted this as a local fraction, which might be local dust or maybe also alluvial. So I think this is coming from the catchment of the lake. Okay, so siliciclastic proxies on the one hand and the grain sizes on the other hand. And we did then a principal component analysis, and I show here only the major results. You see here the first principal component, which is a compilation of all these siliciclastic proxies which show a remote southern origin. And this curve here shows you the higher the curve, the more material which is deposited in the lake is coming from the south. So this is the information of this curve. And you can see here 10.2, 8.2, 6.6, or 4.2 are signal or phases where we can observe increases in this southern provenances. So when you match this with dust or with the grain size principal component, this is principal component number 3, then you can see here that this increases in southern events, that they coincide with grain size fining, and our interpretation is here that grain size fining and southern increases in provenances show southern or Saharan dust increases into the lake. So this is our interpretation. So when you go now back to our hydroclimatic signal, then you can see, which is coming from the Atlantic, not from the Sahara, then you can see that for many of these phases we have a coincidence, for example 8.2 or 10.2, but we've got also phases where we have not this coincidence, for example at 9.4 or 7.3, where we've got aridity from the Atlantic, where we have got aridity from the Atlantic but no dust increase. So, and this give us an idea that the dust record might be from the sub-Sahara, or that there might be also a driver which is maybe from the sub-Sahara, and this I want to show you in the next picture. I focus here on two humid phases with decreased dust deposition from the south, which are marked here with the blue bars. And and you can see that they are erupted by a short dust increase around 8.2. And when you now go to the eastern Mediterranean Sea, this is the record B, which is also marked here in the slide. Then you can see that this dust decreases in the blue bars, that they coincide with subtropel formation in the eastern Mediterranean, which is, as many people assume, also driven by sub-Saharan Nile waters. So this could be a sub-Saharan signal. And currently published, a paper from the Western Sahara shows also this increase in aridity at 8.2, which is also visible in our record, which is from the Western Sahara. But you see here also keeping age uncertainties, age problems probably in mind. You see also these humid phases, which are here marked by the blue bars, that they are maybe probably also in evidence in the Western sub-Saharan region. So, come already to the conclusion. We have got a lake record 20 meters for the last 12,000 years, with an overall increase in Saharan dust from the early Holocene to the late Holocene. We have got multiple millennial scale Saharan dust events during the early and the mid-Holocene, and the major phases coincide with Mediterranean aridity, but especially we see millennial dust peaks at 10.2, 8.2, around 6, but also at 4.2, which might indicate a sub-Saharan origin. Okay, thank you very much for your attention.
Could you add some information about your age model that you used to fit your events into the Holocene timescale?
Yes, this age model is especially done by my colleague William Fletcher, which is very close to you. Maybe he can give you a short comment on it. So we did it on 14C dating on pollen concentrates, and afterwards we did Bayes and age model of this data which we received from pollen dating. So we match it with I think with 3 or 4 samples which were from terrestrial macro remains, but the other one were from pollen dating.
So was the transition gradual or abrupt? So you started with that, and we didn't get much light to that.
I think it remains an open question. What we can see is that we have multiple peaks, which shows in an overall trend abrupt increases in dust, but the overall pattern is gradual from the early Holocene to the late Holocene. So I think it's a mixture of both records which I've shown in the beginning. So a compromise, if you want.
Okay, so I have a question. Did I see correctly, this core is 19 meters long?
Yes.
So you could do, for the Holocene, you could do an incredibly high resolution analysis with the XRF and so on.
Yeah.
Down to sub-decadal scale, I would think. Is that in the planning?
We need funding. But theoretically it's possible, I think.
So, thank you very much, and I think I want to play this as more of a thought experiment, really, than a lot of hard facts. And so what was motivating me to start with thinking about this was some of the, sort of looking at some of the results that, say, Christof was showing from Peter Domenical's work, where there's an abrupt transition at about 5,500 years ago, and then listening to Bill Ruddiman saying that that's the start of the Anthropocene. Whether that's I'm not going to go into that argument, but at least people have suggested it, and it made me think, okay, well, maybe humans might have played a role, therefore, in the collapse of the African humid period. And so the African humid period is a little tricky to model, and I'll say it like that. And clearly there are discussions about exactly what its nature is. And I'm going to sort of skip over those, and instead use more of a motivation of a piece of work that came out earlier this year, which surprised me from a historian. And I like the phrasing that historians use, so I'll read it out. The Neolithic quest to maximize the Anthropocenic productivity may have pounded the final nails into the net primary productivity coffin, and the desertification of the Sahara was, effectively caused by humans. And I think that's a little over the top. But it at least motivates me to think, okay, well, how could we go about even testing this question? And the first thing you need to be able to do to see if there are changes in the start of, or changes in the date for the collapse, is to be able to say when the date for the collapse could have been and actually predicted. And so I'm going to go through a little bit now of explaining a model and the way I've done to try and predict it. And I'm going to try and go through it fast so that I can get to the more fun bit at the end. So, but do ask questions if you don't get things, and I'll happily talk to people after. Right? And so I'm, rather than using a GCM, because I know that GCMs are going to find it hard to do, I'm just going to use a little toy model and say, okay, it's a toy model and I'm doing a thought experiment. I'm using Zengor Liu's model, which has this strange, it's called noisy bistability. So instead of being like abrupt as in a trigger point or gradual, it's sort of gradual but with noise on top of it, and the noise flavors it, so it can show tipping points but also has a gradual underpinning underneath it. And all I've done is taken his model and added in a background rainfall that's dependent on precipitation and carbon dioxide forcing. In this case, I'm using this more as a sign of glacial climate response, but I'm using carbon dioxide radiative forcing. And so I can set up this model, and there's a series of parameters I don't know. There's 7 that I don't know, and there's 2 input time series, and it can run really quickly. It's a stochastic model, so you need to run it a lot of times, and I feel obliged to show some results from the individual models. This is just 100 instances of a model, and I've been using it over the past 230,000 years, and starting then and just running it forward. And as you saw, it's only 3 equations. It can go pretty fast, and so I don't need to worry about that. And down on the bottom are the input time series, but hopefully you realize about precession. And what you can see is that there are 7 sort of green episodes that happen, and we observe 7 green episodes. I'm using sat propels to trigger them, but it's really, or to mark them, but I'm not looking at the timing, just the existence of there being 7 green episodes. Right? And that's very good, but as I said, there's lots of unknown parameters, so I'm just going to do a scattergun approach and run 100,000 different ensemble members, all with different parameters, and loads of them are wrong and don't replicate anything that could be considered as being plausible. And the ones, but I'm going to keep the ones that have 6 green events prior to sort of the last glacial maximum. And of my 100,000 members, only 12,000 actually exhibit something that is not implausible, also I can't discount for just being wrong. And so I'll take those and then look at the spread across the remaining ensemble members. And this is this plot down the bottom. Ooh, that's not right. This is the plot down the bottom, and what you can see here is that there's a black line, and that's the median, and then there's some grey, and that's giving you the 5 to 95% confidence interval. And it's really hard to see the grey most of the time because they all do most of the same stuff until you get right to the very thin end of the plot in the Holocene, where sort of all bets are off, and the ensemble does lots of different things. Okay, and in fact, so if we trained our model and we're standing at the LGM and thinking, okay, well, is there a tipping point coming up? Looking at the past 200,000 years, we're able to say, yes, there's a tipping point. But we would not be able to, even if we knew the future forcings, we would not be able to say that we would actually cross that tipping point and collapse the Sahara again. And so over a third of the models don't, or a third of the ensemble members don't actually collapse. And I'm not going to plot those because they're clearly wrong as well. And so just this bottom panel is a zoom in on the slide, sort of on this last period. And all I want you to take away from this is that there's quite a lot of spread, right? And I think what this is saying, that the collapse of the green conditions at the end of the African humid period just have inherently low predictability. Right? It's just something that even with the best models, doing sort of perfect model experiments would be really hard to do. And so, unsurprisingly, I take some solace from that the models, that the full GCMs are doing it badly and having troubles with it, because it's just a really tricky problem. But with this, because I'm using a toy model and I know what's going on, I can look at sort of the sensitivity and build a time series of the time it would collapse. And the way I'm doing this is by knowing that if I remove the noise out of this stochastic model, then it has a nice potential well that's defined by the input parameters, and I can just look at where the potential well moves from closer to a green state to being closer to a desert state, and I can just do a histogram of where that happens. And if I do that histogram, then you end up with a big onset of the African humid period at about 14.7 years. This is this big spike in the thin blue line or the thin black line here, but less predictability in the collapse of it, and they're collapsing it, and they ought to be collapsing at slightly different times. And in red here, I've got an estimate from my colleague Katie Manning of relative population. And so this is coming off carbon, off a kernel density estimation of carbon-14 dates. And so so you can see that there are slowly people start moving into the region. There's a dip, and then another population boom, and then as the climate deteriorates, the people can't live there either, and so the population goes down. And so, zooming in on this, I'm now going to take those two lines and zoom in on them so you can see more of the features of the sensitivity time series for the collapse. And so, now the black line, now my black sensitivity time series, that's this bottom one, and you can see that it's got these sort of, it's quite distributed, but there's 3 peaks, and the biggest of those peaks is about 6 1/4, something like that. And so there's a dotted line at 6 going through, and so it's before that 6,000 years. And you can see with the population that I'd previously shown, you've got these. The first peak is hunter-gatherers, and then they start dying off, and then the pastoralists start coming in, and the pastoralists start expanding across the region to have another population boom, and then they move away as the climate deteriorates. And so, at the moment, that's fine, but then how do we compare that to observations? And Christof showed Tim Shanahan's data compilation, and so I'm using this data compilation up here, and I've just done a histogram of where that subjective definition of the collapses across the region. And the population is only stuff from the Sahel upwards, so I've cut out so the observations is only stuff from the Sahel upwards, and I've done this histogram. And you can see that there's clearly a system's collapsing, and in some places it starts at maybe 7.5, and there's a big peak, and the majority of the records go at, say, 5.5, okay? And so, going back to this first bit of the humans triggering it, well, if humans were triggering it, then you'd expect to see the observed date of the collapse, or the date you would find in observations, to be earlier than the one you'd expect from the simulation, and that's clearly not happening here. And so I don't find any evidence for a human trigger, and in fact the model implies that the Holocene collapsed later than it should have, and possibly therefore because of the humans. And so I'm going to spend a minute or 2 minutes, describing what I think what these peoples are doing, right? And so we're knowing this is pastoralists, and so the pastoralists come onto the scene round about at this sort of time, and they're bringing their cattle. Then agriculture itself is not around, so there are people migrating herds, as you would find in the region anyway, but they're more proactively migrating the herds maybe. And so pastoralism, so talking to my social scientist friends, the pastoralism seems to have got a bit of a bad rap, and sort of had been painted as really causing grave environmental damage, but I don't think there's much data that properly backs that up. And in fact, the IUCN is actively promoting sustainable pastoralism now to try and deal with some of the climate issues that we're facing. And so I'm imagining that what happens is the Sahara is sort of slowly coming down to a time where it's going to collapse, and then it becomes harder to live there. And so people come in and they invent pastoralism, and they start developing agricultural practices that create niches for themselves, that then can sort of buffer the ecosystem response. And clearly it's a climate vegetation coupled feedback problem, and so by saving some of the ecosystem, then you're also starting to save the climate, and you can end up delaying the collapse. And I think, so I'll just sum up now, that I came into this thinking of it as a thought experiment, without not really expecting to be able to prove anything, to be perfectly honest. But what I certainly do not find is any evidence that humans act as a trigger and induced a collapse in the system. And supposing that the model I've built is actually perfectly right, it would in fact imply that there's a delay in the system. And if humans were causing that delay, then you would need to know that there were enough humans there, and the population peak of pastoralists, I reckon they're doing the right sort of thing in the right place at the right time, but whether they were just doing enough of it, I don't think I'll be able to answer. And I'll just wrap up by what I wasn't really expecting, but playing with this is, I think that maybe this is actually a positive story about how early peoples were able to deal and adapt to climate change. And maybe even if this delay is plausible, maybe even start mitigating the climate changes they're seeing. And I'll stop there and stop wittering. Thank you very much.
Nice idea, but did it occur to you that your toy model is just, too simple?
I don't think it. I wouldn't say it had not occurred to me. I don't think there's enough data to be, and the models clearly have biases, that you could do an awful lot better than this toy model. And I was not actually expecting the toy model to really indicate much, but I went into it, to be perfectly honest, trying to learn how to code Python. And was using this as something to do. So it clearly is too simple. But does that invalidate playing the thought experiment? I think not.
So I want to start by acknowledging Jess Conroy for the collaboration, and also for having me join here field trips, because I think that for people like me who are climate modelers and they work with proxy data, it's very important to gain a little bit of a perspective and much appreciation for how this data is collected, and sort of share the excitement and the fun, and also the stress and the hardship of collecting data. So with that, I also want to acknowledge all of you and NSF for the support, and Fei Jin, who's also a collaborator in this project. So in shifting years, I'm talking about the tropical Pacific climate. We know that it varies at multiple timescales. So for example, the mean state varies at multi-centennial to decadal variability, decadal scales. And if we want to characterize this, we can take the difference between the, if we want to characterize the mean state, we can take the difference between the warm pole and the cold tongue region, and then we can look at the low frequency variability of this in the 20th century. So you see we have periods with weak zonal SST gradient, stronger zonal SST gradient, etc. The other main variability timescale, of course, is Enso, interannual, and that also varies at decadal timescale. So if we do a 15-year running standard deviation of this, you'll see we have the characteristic mid-century lull in Enso activity, and then an uptick after that. So these timescales, they're not independent, they're interacting with each other. So it's either the mean state affecting Enso or Enso affecting the mean state, or both. So when it comes to how the mean state is affecting Enso variance, there's about a zillion papers on this. But here I'm going to focus on one simple conceptual approach, and that is the one of the maximum potential intensity of Enso events that was discussed in general in 2003. And this is a very sort of simple idea that the intensity of Enso events at any given period is limited by the zonal gradient between the SST of the wormhole, or the radiative convective equilibrium temperature, if you like, and the mean SST at any given longitude. So this is what you see here in this plot. On the x-axis, we have the longitude at which an Enso event peaks, and on the y-axis, we have that peak SST anomaly. This is DJF. So all these open circles here are from a model, SSC, CSM4, and then the red dots are from HADAI SST. So the point here, so this just shows how big the events are and where they peak. So the Eastern Pacific, the big Eastern Pacific events would be on this side. The smaller Central Pacific events would be on this side. So now if we actually plot this curve of this maximum potential intensity, in black is for the model and in red is for the HADAI SST reconstruction, then you can see that by and large events are limited, are capped below that curve. So the point of this is that those two time series that I was showing before, this zonal SST gradient, that's low pass filter to remove Enso, and the running standard deviation of Enso, then they would be positively correlated. So if you have a strong SST gradient, then you can have big events happening, right? Now, let's go to the opposite now. How could Enso variance be affecting the mean state? So this is based on the fact that Enso is a positively skewed event, phenomenon. So if you look at, I apologize for but clearly, anyways. So this is actually Niño 3 SST anomaly. So this is the evolution of the 5 strongest or 6 strongest events since 1950. So you see it's the El Niño event and then the following La Niña or neutral conditions. But El Niño events are larger than La Niña. So after this El Niño La Niña cycle is over, then not all of the anomalous heating is cancels out. So there's this residual nonlinear heating that acts to warm the cold tongue, so thereby decrease the SST gradient. So this is in a model, you can actually calculate that. So this blue line there is the difference in SST. On the x-axis you have latitude between decades of strong Enso variance and weak Enso variance. So you have this dipole structure. This just means that the cold tongue is warmer, and then if you calculate in the model this nonlinear dynamical heating that is residual after those El Niño La Niña cycles are over, then it has the same dipole structure that explains some of it warming. So this idea you can find it in literature as Enso rectification on the mean state, and it doesn't have a zillion papers like the previous issue, but still it has quite a few papers that you cannot see here. So but the point here is that in this case, if this is sort of dominating as a mechanism, then those two time series would be negatively correlated, because now if you have strong Enso variance in a specific period, then those events are rectifying on the mean state, so they are warming the cold tongue, so they are decreasing the SST gradient, right? So I want to ask this. So the question I'm asking is, which one is it? Is it positive or negative correlation? So I'm starting here with, I had a summary here. So if the mean state is primarily affecting Enso variance, we have positive correlation. If it's Enso variance that rectifies and warms the cold tongue, then we have negative correlation. So the answer to which one is it is it's a little bit of both, and that is okay, and that's what I'm trying to convince you today about. This might move. Here it is. So this would be a Hofmöller diagram now of, so this is longitude and this is running standard deviation of Enso. Clearly that just says that, you know, maximum variance of SST anomaly you have in the Central and Eastern Pacific. That's where Enso is happening. This is the mid-century lull in Enso activity I was talking about before. And this is the zonal Sst gradient after removing, of course, Enso, and this would be their cross correlation. So you have periods of increased Enso variance where you have positive correlation, and in other periods it's a little bit noisy, but with decreased Enso variance and positive correlation. So so that's fine, but or not so fine, but it's a little bit curious. So the problem with this is that these are short records. They are different reconstructions and reanalysis, they don't agree necessarily with respect to these zonal Sst gradients, and these are short records. So what we want to do is ask for some help, and that we can do that with proxies and models, of course. So when it comes to proxies, the fact that proxies have different resolutions, in some issues it might actually be a problem or a challenge, but in this case we think that it's actually an advantage, meaning that they are sort of independent in what they're showing. So for Enso variance now, to approach this or study this problem a little bit more, for Enso variance I'm going to use coral data. I'm pressing this and this is not moving. Wait. Here. Okay, so for Enso variance I'll use annual and subannual monthly resolution coral records from the West Pacific, Central Pacific, Eastern Pacific, and these are data by McGregor, Cobb, and Dunbar. So this is what you see here. It's a running standard deviation of Delo 18 now from these records in the West, the Center, and the East. So if you want to compare this with Hadai SST, then you can go along these dust lines and indicate where these corals are. Without going into too much detail, we do see these, these lull in the mid-century, then an uptick in Enso activity. Whatever we see in this record, there is a good consistency with what the corals are showing, and that might not be surprising, or it might be. And for the zonal Sst gradient, I'm going to use the Manonal reconstruction. That would be filtered. And it may change, and you may see it, or you may not. Here we are. So this would be the green line there. That's Manonal, and then the black line is the Hadai SST. So what I'm trying to do is that what I was showing to you before, but from Hadai SST, I want to see if I can see the same sort of alternating correlation signals when I do this for between proxies and proxies, and without having any of those Hadai SST. So here is what I'm trying to sort of recreate, and here's what I'm recreating. There is, of course, since the corals are along these lines, they would be, the signals are more concentrated there. It's the linear interpolation in between, and you can see that you have those sort of, this indication of these alternating signals, and then the previous period is positive correlations. So I think that's okay, and that's some people might actually believe more the proxy correlations rather than this one that comes from inevitable filtering. So this is primarily the Central and Western Pacific. I'm not showing you here the Eastern Pacific, but I will. And the problem with the Eastern Pacific, if it shows, is that there's no agreement between these, between the proxies and what Hadai SST says. Here it is. So there's nothing here, or it's a little bit problematic, and I want to say that I think there's two reasons for this. One reason is because that's a low resolution proxy. It's an annual coral record rather than the monthly coral record, and also it participates in the reconstruction. So they're not as independent as I would want them to be. Now, the problem with showing correlations, especially when they're changing signal, is that no one feels comfortable with it, and I don't, or at least I don't feel comfortable with it unless there is a physical mechanism that can explain this. And I alluded to these mechanisms before, but now I want to provide a little bit more context using a climate model. So this is CCSM4. So this is a period now of strong Enso standard deviation that you see here. This again running correlation, right? Running standard deviation. This is the Zonal Sst Gradient, and this is their correlation. If you could see these here, we're Central and Eastern Pacific. So now, because this is a model, I can go and compute the nonlinear dynamical heating and all these fancy variables that models give us. So that's what it is, and as we know, it would be negative in the west, positive in the east, that's fine. And then if I do the correlation with the zonal SST gradient, then I have again this characteristic is dipole structure in the correlations that explain what I see here. Now, take my word for it that as I think you've done with many things here, since the figures are not showing very well, but anyway, take my word for it that in periods of weak Enso activity now from the same model, these correlations are positive, much like we were seeing in the period of lull of Enso activity in Hadai SST and in the proxies as well. So I think it's time for me now to jump to conclusions. And so the point of my talk was that the relationship between the tropical Pacific SST gradient and Enso variance, it varies spatially and temporally, and that's okay because there is legit mechanisms to support both signs of these correlations. One idea would be that DSST determines the intensity of Enso events and thereby Enso variance. The other idea would be Enso rectification on the mean state. So we did see capturing this relationship in the proxies. We are extending this now to other periods of the Holocene. And of course, modern analysis shows the importance of nonlinear dynamical heating. So I want to say that the relative strength of these two mechanisms is important. And even if not just for understanding what Enso is doing, this is here my shameless plug for our paper that was published a few months ago, that assessing the skill of models in simulating this mechanism has implications for future climate change pattern in the tropical Pacific. And clearly what we need to better assess this would be high resolution proxies, more of them in the Pacific, especially in the Eastern Pacific, if that's possible at all. Thank you.
You argue for maximum potential intensity as a control of Enso variance. However, for example, in the 20th century, most of the events actually, the amplitude is much lower than maximum potential intensity. Perhaps 1997 is the only one that sort of reached this MPI. There are other ways that delta SST can control Enso variance, for example, for Bjorkman stability index, or could you comment?
Yeah, no, I can comment that I agree with you. I just the point of the maximum potential intensity, as you very well point out, is that it's one of the I'm looking into models for this to see what they're doing. The observations, you're right about that, but the point is that, again, I'm saying that it's a little bit of a short record for us to know, because you saw in the model, and you saw in Hadai SST that, some events are above that, some events are below that, but and in many models as well, if you see the same plot, that I showed, then indeed some models, they are very well below that curve. So yeah, very, very much so. That's why it is, I don't think that that's the only way that it controls it, but that would still give me a positive correlation between those two which would be on the sort of opposite side of what I would expect from the Enso rectification hypothesis, right? So that's more where I was getting at by choosing that sort of metric, but you're right.
Thank you so much for making it to my talk this afternoon. And I am going to be talking to you about research that I am finishing up with my PhD with Kim Cobb at Georgia Tech, and excitedly will be defending here in less than 2 weeks. So I'm following up on some of the research from Kim Cobb's fossil coral reconstructions of Inso. So as you guys all know, in 2015, 2016, we had one of the strongest El Nino events on record. So we see here, this is the NDJ anomalies, SST anomalies in the shading, and the precipitation anomalies in the contours. And this was one of the strongest events that rivaled the 1997-98 events, and then before that, we also had the 82-83 event. So we have all these extreme events that has really brought the question about what's fueling these extreme El Nino events. Is it part of anthropogenic climate change, or is it just part of natural climate variability? And if we look at the instrumental records, so this is SST from the Nino 3.4 index, we do see stronger variance in the last 50 years, but the instrumental record only goes back to the late 1800s, and you can argue that it's really only reliable back to around 1950 or so. So really the instrumental data, it's just not long enough to really put these extreme events into context of natural variability. So I think a better way to phrase the question with this is looking at, is Enso sensitive to external forcing? Because with this, then we can actually look at whether it's sensitive to natural as well as anthropogenic forcing. Because we can go to the mid-Holocene. It's a very good testing ground to test whether Enso is sensitive to a natural forcing. Because in the mid-Holocene, the precessional forcing was different than today, affecting the changes in the spring-fall insolation, which is the critical time period of growth and decay of El Nino events. And the thought is that it could perturb the seasonal cycle such that it prohibits El Nino events to occur, and so that we see a reduced Enso variability in the mid-Holocene that many climate models actually do pick up. And if we look at some of the proxy data already published, in the Eastern Pacific, we have, there are some Mullis records from Carrier in 2004 that show the reduced Enso variability around 4,000 years ago, as well as some single forum records from Kutavis also showing reduced Enso variability around that same time. And more recently, we have an oxygen isotope record from a speleothem in Borneo that is also showing the most reduced Enso variability around 4,000 years ago, and may actually link this to the boreal fall insolation on the equator. So I think we can now break out this question into two parts. So was Enso reduced during the mid-Holocene when precessional insolation was different? And are Enso extremes strengthening with anthropogenic climate change? And so I'm gonna look at coral oxygen isotope records from the central tropical Pacific. So the Line Islands, so Palmyra, Fanning, and Christmas Island, they're located at the black dot here. And this is really an ideal location to study Enso variability because you can see it's in the heart of the Enso region here. And also oxygen isotopes of corals, they're an ideal proxy for looking at Enso variability because they vary with both SST and rainfall. And when an El Nino event occurs at this site, as you can see, the SST increases as well as you have increased precipitation, and that actually drives the oxygen isotopes both lighter. So in a sense, it amplifies the signal. So here I have a whole bunch of modern coral records plotted from Christmas Island. The oxygen isotopes here are plotted on the left, and these are from Porites corals, which we can see right here. And the oxygen isotopes are plotted lighter is up, and that's going to be indicative of warmer and wet conditions and more El Nino-like. And then the heavier are down, and that's cool or dry or La Nina. And you can see plotted on the other axis is SST. Each of the different colored lines are a different coral, and in gray is the SST. And so you can see, one, that all the corals reproduce each other quite well. They reproduce the SST very well, and they also faithfully record all of the last strong El Nino events. But the modern corals in this region, they only go back about a century. And so in order to actually go back and look into the Holocene, we have to turn to fossil corals. And if you're familiar with Kim Cobb's work, she uses these large boulders that are storm deposits on these islands that she cores and gets these beautiful 30, 40, 50 years of record. Unfortunately, she's cored them all, or actually we're finding that the locals have now been destroying these and using them for construction. So we had to turn to an alternative approach. So we're using these smaller rubble pieces that we can collect by hand, and this is a benefit because the unlimited supply of these smaller pieces. However, we're only going to get 10 to 20 years of record from each piece. So we radiocarbon date, uranium thorium date, as well as screen for diagenesis with XRD and SEM on each of these samples. So I'm going to walk you through how I process the data for plotting for the comparisons with all the fossil corals. So here are the modern records for each of the islands, Christmas, Fanning, and Palmyra. And to filter for the Inso variability, I use a 10-year high pass followed by a 13-month running mean. And so that's seen here with the mean year 3.4 index as well. So first what I'm going to do is I'm going to plot everything to a reference period. So this benchmark period right here, from 1987 to 2007, I choose a 20-year window just because that's about the average length of many of my samples, so for a better comparison. And the time period just reflects the most recent time period, most recent 20 years that I have data from all 3 islands. So I'm going to compute the standard deviation from this benchmark period. And then I'm going to compute the standard deviation in 20-year sliding windows across all 3 islands, and then compute that difference with that benchmark period, and that's plotted down here. So the y-axis is now a change in the standard deviation, and I plot it as a % change. And so this is the exact same analyses that I'm going to go through for all of the fossil coral that I'm going to show you. Okay, so before I put it all up here, this is the same y-axis, it's the change in standard deviation in a %. And here is that benchmark period, the 0 line from representing the 1987 to 2007 Inso variability. And then this gray bar represents the full range of variability that we saw in those modern sequences. So the coral records that I'm going to show here, there are going to be many from Kim Cobb's work, as well as Helen McGregor, and all the new sequences that I've added to this around the mid-Holocene time period. So here we go. So now we have a total of over 1,600 years of data back through the past 7,000 years, represented in 38 different coral segments, and they all range from 7 years to our longest record, 318 years. And so just looking at this one that you can see, most of all the fossil coral data plot below our benchmark period, our 20-year benchmark period. So it's just showing that our benchmark period is enormously high. And then this period right here, we are starting to really observe all of the sequences that I added around the mid-Holocene are reduced. The fossil coral, to just step back, the fossil coral is 38% reduced to our benchmark period. And we do see the largest Inso reduction around 4,000 years ago. But we actually must develop a statistical test to determine if these observations are indeed significant. So going back to the first question, was Inso significantly weaker during the mid-Holocene? So I do some tests to figure out where the most reduced period is at, and it's around 3,000 to 5,000 years ago. So I want to compare and see if 3,000 to 5,000 years ago in this blue circle is significantly different than periods before and after. So I'm going to compare it with 0 to 2 as well as 5 to 7. So to do this, I'm going to set up a Monte Carlo statistical test using these multi-millennial simulations of Inso variability. I'm going to use both a statistical and a dynamical model for this. So my null hypothesis is that the observed distributions are consistent with subsampling a multi-millennial stationary time series of Inso variability. And so the way I'm going to do this is I'm going to create fake data. We call it pseudocoral. I'm going to create 10,000 fake data sets that replicate my fossil coral data set exactly. So the same number of sequences of all the same length. And then I can compute those variability, or compute the differences in the variability from whatever time periods in question that I am asking. So the results are going to highly depend on the models that I choose to create these pseudocoral data sets. So I use 2, and they're kind of on the opposite ends of the spectrum, so that the results agree, it kind of adds extra to the results. So 1, I have a linear inverse model that it assumes the statistics from Inso SST and thermocline depth from the late 1900s. And this assumes that tropical Pacific climate evolves as a linear stochastically forced system. And then I'm going to use a dynamical model from the state-of-the-art last millennium ensemble, where I've strung together 10 of their fully forced runs. Okay, so first I'm going to compare 3 to 5K versus 0 to 2K. So with those fake data sets that I made, I'm going to compute all the differences from the coral that fall in those two regions, and there's 10,000 data sets, so there's 10,000 differences, and I plot that up as a PDF, and you can see the 95 and 99% confidence. So then when I actually compute that difference in my real coral data, I can plot that here, and the actual difference is 20%, and so that is way greater than 99% significance from this plot. And I do the same thing, now looking at 3 to 5 versus 5 to 7, and just note the limb, this is for the limb and the LME. And same thing, here we see that 3 to 5 is 17% reduced compared to 5 to 7, which for both models is greater than 99% significance. So we can say that Inso was significantly reduced 3,000 to 5,000 years ago relative to before and after. And so going back to thinking about the mechanism for this, it takes us back to that Shin et al. Plot that I showed you earlier, where they linked it to the boreal fault insulation. And this goes along with some work from Christina that talks about where the Inso growth rate is a function of season, and they show that the El Nino events grow during the boreal fall. So going to my second question, are Inso events more extreme in the late 20th and 21st century? So I do the same thing, but now I'm going to compare all the fossil coral sequences with just the last 50 years and plot that up here. So here's the distribution from the Monte Carlo results, and then the observed distribution is, the observed change is 30%, and you can see that's greater than 99% significant for the limb and greater than 95% for the LME. So with a 30% intensification, we can say that Inso was significantly intensified over the last 50 years relative to the last 7,000. Note I do test different time periods, so I test 30, 50, 75, and 100, and the results are the same for all. And so this actually just adds to some growing support from proxy studies that is showing Inso intensification, as well as models that are now starting to also show Inso intensification, such as the Chai et al. Paper that projects a doubling of extreme El Nino events, although I have to note that's due to an increase in the hydrological response. But I think we also need to be fair with our results and think of some alternative hypotheses, such as, are the corals seeing more rainfall bang for your SST buck? Is it more of a response to the changes in the Delo-18 of the seawater versus SST? Or are we seeing more of a change to CP events relative to EP events? So just to wrap this up, this is a reanalysis of an expanded coral data set from the last 7,000 years, providing empirical support for Inso intensification in the recent decades, as well as reduced Inso variance in the mid-Holocene time period around 3,000 to 5,000 years ago. I think for the sake of time, I'm going to skip through the climate forcing and mechanisms, because that's just up for debate, and would be great to talk to some climate modelers about that, because I think what this work is useful for is to provide targets for these data model comparisons to really probe the mechanisms that govern these Inso extreme events. Thank you.
Yeah, beautiful talk. I was just thinking about going back to Kim's paper in 2003. She showed just with coral data from Palmyra in the last millennium that the variance in the I believe it was the 1700s or late 1700s was comparable to the late 20th century, and there was a statement to that sense that in that case the late 20th century was not unusual in the context of the last millennium. So I'm having a bit of a hard time reconciling that with what you're presenting here.
Yeah, I mean, I know that statement because she says that Inso variance in the 20th century, late 20th and early 21st century is enormously high, but not unprecedented, because there is that one fossil coral sequence that she has that does show high variability. So really, I guess what I'm just speaking to is just thinking about the last 7,000 years. So that's, and then just going through what the statistics say with that.
Okay, so we're interested in understanding past Enso variability, partly because we know that the orbital forcing and the distribution of solar insolation was different in the past. As we saw beautifully introduced in the previous talk, a lot of the background, there are periods such as the period 3,000 to 5,000 years ago which are really coming out as having reduced Enso variability. But there remains a question about the role of orbital forcing over the Holocene. This compilation that came out a couple of years ago, led by Julien Emile-Gier, showed that there was this reduction, but it wasn't necessarily a function of changes in the forcing. In contrast with models, which did seem to show some changes. Okay, but one thing we have to remember with those kind of compilations, it put together records from the East, West and Central Pacific, from corals and mollusks, and you can see sort of illustrated here in these spatial maps of sea surface temperature and rainfall between sort of a nominal normal year and an El Nino year, or February 97 and the peak of the 97-98 El Nino event, that those patterns of sea surface temperature and rainfall change with El Nino events. They change across the Pacific. And what are we doing by mixing these different proxies that have these different sensitivities to temperature and, I've said rainfall, but it's technically the delta H&O of seawater. And we've seen that illustrated quite beautifully in Sam Stevenson's work presented a couple of days ago, as well as Tom Russon's modelling study. So, but yet, there's all these uncertainties, but I guess the observation remains that, for example, in the work we did in 2013, we do see changes in the spatial, temporal, in the tracking of an El Nino event across the calendar year. So, for example, in the panel on your left is along the bottom is the months, and then we see the sea surface temperature anomaly in the Central Pacific, and you can see the sort of typical warming peaking in December, January, neutral years and La Nina years. That's, as I say, for the instrumental record, and then jumping over and doing the same kind of stack for this 175-year record from 4,000 years ago. You can see that there are changes. There's the Enso in the pink there is not as high. It also has a different kind of structure across the calendar year. And that gives us some kind of, at least for me, it's still kind of like, well, there's something going on here. That, you know, what is driving these kind of changes in how an Enso event will track? And so with these questions in mind and wanting to understand how Enso might have changed, we know the forcing's changed over the past 6,000 years. I wanted to focus on a single site, and maybe we can avoid possibilities of complications of delta H&O by combining different locations. And I should add, this assumes that sea surface temperature, delta H&O seawater relationship at this one location remains stationary over time, and that's definitely still a question. So the site is Christmas Island, which is really ideal for a location for looking at Enso. It sits right in the heart of this Nino 3.4 region. Non-continuous coral, several coral sequences, which together give about 255 years of data. Well-preserved material, screened for diagenesis, and the corals were dated by either uranium-thorium dating or radiocarbon dating. I'll just put this up as what these corals records look like. Across the bottom is the calendar year from 1930 up to the present. The grey is a compilation of all the published modern records from Christmas Island, and we've added one sequence at the end there that just takes the modern record back a little bit further through that sort of really quiet period in the 1920s, Enso quiet period, I guess in the 20s, 30s, 40s and so on. We had about 174 years of data in that sort of period around 2,000 years ago. There's not that much material been published from that interval, and one additional 60-year sequence that just pushes the temporal variability back a little bit further, notwithstanding what we just saw in the previous talk. Okay, so that's the new stuff, and the light pink traces are the raw data. and the dark line is the 2 to 8 year bandpass filter on top of that. And I guess sort of you can start seeing some things here, but what does this look like when we put the new data with what's previously, first up, just a little bit more about the records. This is sort of a length of record, histogram for want of a better word, it's not really a histogram, but all the 24 records that are published so far and just how long they are, and I guess critically taking on this idea of Wittenberg and Stevenson from a couple of years ago that you really need longer records to maybe try and characterise the Enso variability. Our records are over 50 years, which is something. And we've increased the amount of data from this one site by about 34%. So what does it look like when we combine the records, these new records I've just outlined, and the published records? Well, by eye, I guess I feel like I can start seeing a trend, and then when we apply some measures of, is there actually a trend there, a Spearman correlation, we can, yes, it does come out that there is a statistically significant trend. If we start slicing and dicing those records, eliminating short ones, keeping just really long ones, the strength of the trend and the correlation improves. If we exclude the 20th century, the trend remains. So I guess the reason for doing that is if the 20th century, 21st century is really an extreme period, is that shifting the trend, it remains if we remove just that modern end member. Not satisfied with that though, because I did mention that we've got radiocarbon dating and uranium-thorium dating samples, which for the radiocarbon dating adds an uncertainty of plus or minus 100 years or so, 150 years. There's also the uncertainty in that all these corals, as I showed, have different record lengths. So we wanted to test, and I meant to acknowledge when I first started Stephen Phipps, who's in the audience, one of my co-authors, for helping out to do this. If we were to sample do a block bootstrap analysis, testing the null hypothesis that the trend is 0, sampling for the uncertainty in the ages of the corals and the uncertainty in the record lengths, and sampling that Enso variability, we get a trend that is significant, so we can reject the null hypothesis that the trend is 0. So this sort of starts indicating that, hey, well, maybe there is something going on here. But just because there's a trend doesn't mean that that's a response to Enso. What if it's just we happen to land on sequences and corals that by chance gave us a trend? And that's what we've tried to test here using an 8,000-year-long control simulation from the Mark IIIL model. We've sampled that 200 or so times using the record lengths that match the corals that we've got. And you can see the probability density function here in the grey, and the 95% confidence intervals on that in the red, and our coral observations sit outside of that. So what that tells us is that we don't statistically generate a trend just by sampling these record lengths that we've gotten. So we're confident we've got a trend in the corals. What could that be related to? One additional comparison we've done is again with the Mark IIIL model, forced, this time with orbital forcing. In this case, they're 1,000-year snapshot simulations beginning 6,000 years ago and coming through to the present. The reason we're doing this is, yes, there's lots of models out there that have looked at 6,000 years ago, but not so many that have the time in between. We did a 2-day bandpass filter as well on the NINO 3.4 region and calculated the standard deviation there, and yes, again, we get a statistically significant trend in these snapshot simulations. We've repeated this using a Ford model based on both the salinity temperature relationship from the Thomson work and also based on the calibration we've got for the site at Christmas Island. And this observation of an orbitally forced trend in Enso variance was also noted in the paper by Liu et al. 2014. I hope I said that right. And I've just been speaking to people here about doing a comparison as well to look at this a little further. Okay, so in the Mark 3L model, what is driving this? Plotted up here is the trend in the August mean sea level pressure and the surface winds over the past 8,000 years in this case. And we can see that there's a trend to a weaker Asian monsoon. A stronger, I'm slightly dyslexic, so I get it all backwards. But stronger Asian monsoon in the mid-Holocene, stronger Walker circulation, making it harder to generate an El Nino event. Another way to say that is we've got a trend to a weaker Asian monsoon, weaker Walker circulation, and increased Enso. This is obviously for those snapshots, but this observation has also been made by Zheng et al. In 2008. So I just want to give you a quick preview of what's to come. I've got plotted up here a modern coral stack from Christmas Island. I think I showed that previously. The ERSST in the dark on the right-hand side of the plot is the 175-year record that we had. And then what's continuing on in the left of the plot in the lighter blue is an additional record that's I'm just generating and refining from one of these coral microatolls. It's there in the picture. I don't know if I stand out, but I'm standing right in the middle there. I'm not particularly tall, but I think you get the sense of that grey circle is the size of this coral that's generated this record. Preliminary dating suggests they do overlap. I don't trust that yet, but I guess what's standing out is this weaker Enso. And seeing as it's kind of, now the third last talk of the last session of the last day, I'm going to take some liberty to kind of see what we can do with this. So, as some of you from Europe will know, that tonight is the final of the Eurovision Song Contest, the biggest song contest in the world, been going for 60 years. Australia, for some reason, is in it. AU for EU, so vote for Australia tonight, everyone. But the theme for this year is Celebrate Diversity. So I think we can rename Eurovision to Enso Vision and celebrate diversity of possible Enso flavours. With records this long, we can maybe start to build up a picture of what Enso and how Enso has changed and what flavours might be contained in this record. So enjoy Eurovision, everyone. I'll leave you with my conclusions.
I'm trying to reconcile your talk with a previous talk, and the previous talk point was there was a minimum in Enso variability in mid-Holocene, and you are saying that there is a trend with increase in variability towards the present. Any explanation for this difference?
Well, I think, I also see a reduction in that 3,000 to 5,000 year period, so that's the first thing. In that sense, I don't think that there's a difference. There is, like the ITCZ does migrate north and south across the Line Islands. I don't know, but I wonder about different delta 18O relationships between the different islands. I think, some strontium calcium will help to look at that. I think record length matters. If you're sampling short lengths versus long lengths, I think that was one of the tests we did was excluding the shorter ones and we get the stronger trend. We should probably try it. I think we did try it the other way around of excluding anything long and seeing if we got a trend. I can't remember, but I can check the results. But I think actually it's a critical mass of data. I think that Wittenberg and paper and the stuff that Sam Stevenson's done has shown that you can sample with short records. You can sort of missample Enso, and I think as we build these data sets, I think we're going to constrain it a lot more. I'm not sure if that fully answers your question, but
I would like to affirm the importance of celebrating diversity in Enso, because it's actually an idea that Christina right here and Pedro proposed a couple of years ago, that you could potentially explain, at least in models, the apparent reduction in mid-Holocene Enso just by shifting from Eastern Pacific to some more Central Pacific Enso. And it's important to remember, as much as I love the Line Islands, that they have a really hard time telling an Eastern Pacific from a Central Pacific Enso apart. So I think it should be a renewed call, if we are really interested in Enso flavors, researchers to start digging in the east a little bit more. And I know that it's a tough place to be a coral in the Galapagos, but it's really critical that we develop more records from the east.
Yes, and I know Julie Cole and Sandy Tudhope have been doing drilling, and I'm looking forward to the results. And I've kind of wondered about our long record running it through Mandy's kind of decision tree and seeing if we can pull out flavours. So I don't know.
Good afternoon. It's a pleasure to be here. I'd like to thank the organizers. We have a remarkable facility here, and thank our session chairs. And we'll go on with this. I'm going to talk about the causes and consequences of the 4.2K year event. We have the fortune of having one of the pioneers in looking at this here with us. Harvey, thank you very much for coming. And this is just the title slide. We're going to look at causes and consequences, which are traced by these pictures that I'm sure you can't really tell what they mean, but we'll go into that during the talk. And I want to acknowledge many of the people who have contributed to this work through data and ideas and talks and emails. So let's move along. Okay, what is the 4.2K year event? Now, I was surprised. I ran into some people. I gave a poster on Wednesday who didn't know what it was, so I put this slide in. It's one of the major Holocene abrupt events. It's marked by the collapse of the Egyptian Old Kingdom and the collapse of the Akkadian Empire at very close to the same time, certainly within the uncertainty of the historical records we have. Both are marked by evidence of hydrologic stress, and the Egyptian Empire, the Egyptian Old Kingdom, ended with the first intermediate period, which I'm going to use as kind of a general marker, which was a period of intense disarray in Egypt and has been variously ascribed to climate change. It appears in widely distributed proxy records, and as I define it here, it's a sharp event. It's transient. It's about 200 years long. It lasts about from 4.2 to 4,000 years ago. Now we talk about consequences. What am I asking? Did an event occur? What are its characteristics physically? What would a climate map look like? What are the causes? What are the processes involved of the chain of mechanisms? Can we get at that? Our approach is to look at proxy evidence, in part, which is admittedly scattered, often ambiguous, and certainly uncertain to varying degrees. We're going to establish a broad idea of what happened physically and interpret that evidence in light of climate model results, specifically looking at what could make that happen. Right, here's a kind of an overview slide of some basic characteristics. Some of the graphs on here have been shown for many, many years. On the bottom, you'll see here I forget which one's the pointer. We'll try that. Okay. This is marks the 4.2K year event as seen by the first intermediate period. It overlaps exactly most proxies very closely. This is Egyptian record. You can see this is the blue line is the Old Kingdom, and these are the pyramid builders, and that society pretty much collapsed, and there's lots of evidence that there was societal upheaval and certainly political upheaval in the Akkadian Empire. We have two records here that are rather new. These are from my co-authors, Matt Salzer and Malcolm Hughes. I neglected to mention my co-authors. Dirk Verschuren is another one. The top record is a tree ring record from high elevation trees in the mountains of California. And we can see this deep dip during the event in tree ring width. The record ends because the trees died. There is not a sufficient population to make this record after that point. We see a tree line record from the same region. These are trees from very close to the tree line, very high, above 3,000 meters in the mountains. The elevations on the left shown in green. You can see this very sharp fall at the same time. The blue dots mark death dates of trees. So the entire population at high altitude died. These are bristlecone pines. They die very slowly over a period of probably decades because they starve as it gradually gets colder. They cannot. Their resources become depleted. Tree rings, of course, can record meteorologically cold winters. This is a record of monsoon strength from the North Arabian Sea, so Southwest Asian monsoon, if you will. There's many, many records that suggest it was dry at this time, and certainly This is well known. This is an older record. This is Delta 18. But we can find other records that look very similar to this from speleothems, and you'll see some of those. Another famous record is the dust record from the Gulf of Oman. This is dolomite that's traced back to Mesopotamia, suggesting it was arid, as supported by other records, notably the evidence from Mesopotamia. All right, so let's look on a little bit more. So we're seeing records here. I want to stress that we see evidence that it's cold, at least in western U.S., and certainly that the monsoon in southern Asia declined. There's many more records that suggest it was cold across much of North America and into other parts into Eurasia. So getting this idea that it's cold in the extratropics of the northern hemisphere, and certainly a monsoon decline, which caused aridity, regional aridity, and some evidence of aridity in the higher latitudes of Eurasia, and as we see here. So, all right, let's do that. Whoops, wrong one. Okay. Whoops, go back. Okay. Now, one of the questions we had was, can we really justify that there was an event? This slide compares some high-resolution proxies. You can see the time scale is relatively short. This is about 1,000 years shown here. And each of these records has been normalized to some extent. The upper record of frost rings from those trees I was talking about. Frost rings are caused by cold periods that occur during the summer, especially at the end of summer, when it gets very, very cold before the tree is shut down, and we get narrow rings or actual damage to the tree. There's no trees in this gap here. This band marks the 4.2 K-year event. We can see these deep periods of evidently very cold conditions that are recorded in these, mostly in fossil wood and relic wood that was found in the mountains and dated much as the talk we saw earlier. These two records are speleothem records. This is from northeast India. Down is dry here. This is a very well-known record from Max Berkelheimer from northwest India. This record is one you probably haven't seen in this context. This is from Indonesia, an Indonesian speleothem from south of the equator. Now, what's interesting here is down is wet in this record, and we have this dry-wet offset. And why would that happen? Why would we get it dry on one side of the equator and wet on the other? And we have another record here. This is from the North Iceland ice sheet, from the ice shelf there, very shallow water from Marie Alexandre Sicre. And it's a very high-resolution record. It's pinned to volcanic markers, and so the time scale is probably pretty good. The volcanic markers, anyway, it's well dated. You can read about it. And this is about a 1 degree C drop here, we see. So we got more evidence that it's cold, and as I say, there's more proxies. I'm not going to go into all of this, but reiterating the idea that the monsoon had across the southern Asia had failed, but that it's wet south of the equator in Indonesia there. We get this idea of a pattern when we really include lots and lots of different proxies. And this is a map of the world. I hope you can see the outlines. I've got cold is blue on this map, drier is more arid is orange, and more rain is green. And I've just put a circle around that particular area where the speleothem from Flores came from, down there. And there's evidence of aridity there. And this is just kind of circling where we find different proxies showing different things to get a rough idea of what's happening. Now, we were talking about consequences. So now let's go to causes. Why would this sort of thing happen? Or does it make any sense? I want to stress, we're going to look at some dust-enabled climate model results. We're going to compare with and without modern dust emissions to get an idea of what dust does. You have caution. I want to stress that we should have caution evaluating these results. Dust modeling is extremely complex. There's many interacting processes, as you can see. Radiative effects, transport, mobilization processes, many. And so results from different models can vary. Results changing any one of these parameterizations to change the results a little bit. But some features appear commonly, others don't. And we'll look at some of those commonly appearing. I'm going to show you some results from some simulations, taking in mind these cautions. This is two results. These are changes in air temperature from two of these runs. In both of the results, the colder temperatures are marked in blue, which is very nice. Warmer is red. One of the first things that jumps out is we have widespread cooling over North America when there's lots of dust coming out of North Africa. North Africa generates most of the dust on the planet. So you increase the dust, and the net effect is to cool the northern hemisphere. And the bottom is another model. It's got the same sort of a pattern in it. It's blue. The magnitudes are actually fairly similar, although the color tables are quite different. We see typical reductions in the northern hemisphere of about 1/4 degree to 1 degree. It's more systematic over land. Models disagree over North Africa, and that reflects this sensitivity to the radiative properties. What is that?
2 minutes.
How much?
2 minutes.
2 minutes, okay. All right, these are precipitation changes. And here in the upper panel, dry is blue, and in the lower panel, orange is dry. So orange is blue. Dry is blue in the upper panel, orange is dry in the lower panel, and wet, and you'll figure it out. Red is wet at the bottom. And what do we see? We see that the ITCZ, the whole tropical rain belts, have been shifted south, and we get a pattern that looks very much, if we also fold in the temperatures, what we were thinking we got from the proxies. What does this tell us? This tells us that lots of dust makes some of the elements we were talking about when we were looking at the proxy data. And in fact, if we look here, we see in this box, we can see this dipole appears too. And is this a product of the ITCZ, or the rain belts moving? The cold climate system is shifting south. So lots of dust makes the pattern we were looking for. Where are we going to get a lot of dust? We can get a lot of dust from Mega Lake Chad. Mega Lake Chad is a huge lake, 400,000 kilometers. It receded very rapidly after about 5,000 years BP, after slowly declining. This is the subject of a poster I gave on Wednesday. I'm not going to go into it too much. But what we find, one of the things I do have to mention is that the northern part of the lake, the Baudelaire Depression, is now the dustiest place on the planet. And if we look at reconstructions of the lake, we can find that indeed there's evidence that it dropped very rapidly at that time. And if we do some other simulations, we can find that dust rainfall feedback from dust generated by the lake causes the lake to drop even faster. So the lake can basically go into a positive feedback, or a negative feedback, if you will, and explosively generate huge quantities of dust on the order of those that are generated today by the entire Sahara, or at least a substantial fraction of that. Okay, so a summary. What are the consequences of the 4.2 K event? Weaker southwest monsoon, there's apparent dipole, cooling over the northern hemisphere, and climate models with increased dust, so the exact same, very similar patterns. The causes: gradual climate change, decreasing North African rainfall due to orbital effects, the recession of Lake Chad due to this regional feedbacks, resulting in very heavy dust emissions, unstable feedback of dust on rainfall, depletion of sediments eventually quenches these events, that's why it's only 200 years long, and certainly other processes are involved. It's rather a simple model we have. This is an instructive result. It's an unexpected, abrupt event in the context of gradual climate change, triggering a much larger event that would cause upheaval if something like that happened today. Thank you very much, and that's the end of my talk.
What I want to talk about is winter, kind of summer's ugly sister, forgotten sister. Going back, I just want to kind of set a bit of a scene, this is a kind of conceptual idea about Holocene climate change. And this is a figure, conceptual idea of Holocene climate change from the old IPCC report, 1990. I think Ray was on the board there. What we have is basically a kind of warming period, Holocene thermal maximum, probably over high latitudes, and probably in summer. And we're always kind of correlating things with summer insolation here. And this relationship is one that a lot of us are still, I listened to many of the talks this week, and I'm hearing it all the time and seeing it very often, that we'll have some kind of figure whereby something's very high in the early Holocene, it's very low in the late Holocene, and then we kind of instinctively want to kind of correlate that with summer insolation. But we should recognize really, and traditionally the way we've kind of developed ideas about Holocene climate change have a bias based on the fact that most of the records that we've been looking at are based on proxies and reconstructions of summer and annual temperature. And there's a kind of ongoing assumption that these annual temperatures are driven by summer temperatures. Often we'll see the summer temperature warming in the early Holocene and also the annual temperatures, so therefore we assume that the two are connected, so actually summer is driving annual temperature. And there are many data synthesis studies now where summer and annual temperatures are basically treated as the same, and they're combined to create some kind of curve which are correlated then or with climate models or with some kind of forcing like summer insolation. And we have constantly, as I mentioned, this kind of confirmation bias where these curves are being constantly correlated with Milankovitch-style summer insolation forcing. So I just want to talk about winter. Just a little bit of Climate 101, just to kind of remind you about the difference between summer and winter. Here we have the energy balance over high latitudes. In summer, well, there's a big surplus, 24-hour daylight in the Arctic. And in winter, we have an energy balance deficit. And in winter, 24-hour night in the Arctic. And so when we're thinking about interglacial climate change, we're really thinking about insolation as a big driver in summer, but it's really where's the heat coming from in the winter, and that's basically a heat flux. That's the equator to pole heat flux. And that's driven by the atmospheric circulation. So I just want to talk about another Holocene temperature conundrum. Seems to be one of the themes of the conference. This is basically all the 3 generations of climate models, going from the early PMIT-1 studies at the bottom through PMIT-2, PMIT-3, and vastly increasing model complexity here. But actually, you'll notice the kind of results pretty similar, actually. We can therefore compare that with data. This is mid-Holocene in the summer, and you'll see these are very uniform. Models create a very uniform response, but driven by insolation. But the data, well, that's something else. That's showing some spatial patterns that certainly don't seem to correspond very well with the climate models. So, to me, it's not an insolation signal, or at least not a direct, simple relationship between surface temperature change and insolation of the type that we see in the models. So what could be one of the missing factors here? And I like this quote from Faegre going back to 1950. And he's basically saying, describing the importance of knowing about atmospheric dynamics and circulation patterns. And that's something that's actually quite difficult to study. We don't have paleopressure proxies, unfortunately. But what we do have is that spatial pattern of temperature anomalies, which we can relate to some kind of circulation pattern. So that's what I want to do now. I just want to zoom in here into Europe. And for the mid-Holocene again, and we'll start with summer, and then I'm going to look for winter as well. And on the left, we have those climate models, simulations. This is the ensemble mean, but every climate model shows this dominant warming in summer. And then we have the pollen climate reconstruction based on over 800 sites, which is a gridded reconstruction of a resolution comparable with that of the models. So you can see the difference there in the patterns of the temperature anomalies. So what's causing this difference? So we can see that Scandinavia warms up. This is what we've known for over 120 years now. How did it warm up? Well, in the models, it's warming based because the summer insolation's increased. But perhaps there's another explanation. And we can look at atmospheric dynamics. We basically can bring warmth to Scandinavia from the south, from the Mediterranean region. And that we can do through blocking. And here's a typical teleconnection. It's called a SCAND, where you have high pressure over western Russia, low pressure over the eastern Atlantic, and it's bringing southerly wind into Scandinavia, something like the 2003 heat wave. And we can correlate that pressure gradient, or the pressure changes, with surface temperature. And that's the relationship which we get. And it seems to be very close to what we are seeing in the data in the mid-Holocene. In the models, well, they don't really show this pattern at all in terms of the pressure changes anyway. In winter, well, the model's on the left again, the data's on the right. The models show more variability in winter than in summer, but as an ensemble mean, these are kind of cancelled out, and it doesn't really show a very strong warming at all. And if we look at the data actually shows a very strong warming in the mid-Holocene. So what would be the explanation? Well, it's not just the pollen data. There's many, many other papers being published about the mid-Holocene being associated with a positive NAO, a strong westerly circulation. So that's very different from the blocking that we're getting in summer. And what are the temperature anomalies associated with surface temperature changes? Well, they have a very strong similarity with what's happening in the mid-Holocene as well. And what are the models doing? Well, they do have a small and a very weak, though, change to a positive NAO. But it's not enough to increase those winter temperatures over Scandinavia. So we have a data model discrepancy. We have an explanation, possibly atmospheric dynamics. That's kind of interesting. But what I also find interesting is that we have the opposite effect in terms of what's happening in the seasons. So in the models, summer's warm, and winter's not much changing. And in the data, summer's a little bit warm, but it's mainly the warming in the winter that's important. So I want to focus on that now. You might ask, well, this is pollen data, so have we got any supporting evidence? And actually, we do have there's always a problem with winter temperature proxies. But there's a paper published, and these are ostracods. These ostracods come from the Mediterranean. And they were there living off the coast of Denmark around the mid-Holocene. And this paper by Vork and Thompson quite a while ago, but they were talking about temperature increases in winter of 5 to 6 degrees. That's probably double what we're seeing in the pollen data. What other data can we look at? Well, we can look at nuts. This is probably one of the first paleoclimate studies ever in the early 20th century. We'll come on to it in a second. But it's basically corylus. Evidence of corylus. And the modern distribution of corylus, this is Scandinavia today, and this is the northern limit of corylus. Yeah. And it has a limit of about -6 to -7. This is the corylus in the climate space of the whole of Europe, and it doesn't grow in temperatures where the winter's colder than -7, really. I mentioned this as a very early study. This actually go back to the earliest 20th century. And Gunnar Andersson, he went out and he actually found and actually made newspaper adverts to try and collect data on hazelnuts that people were finding around Sweden. And this is from the Holocene. Unfortunately, it's not very well dated, but we do know it occurred sometime during the Holocene. The fossil hazelnuts. A very good paper by Heikki Seppo is my kind of inspiration for looking into this. I fully recommend reading it. So this is the dots of the occurrences, the Holocene occurrences of corylus nuts. As you can see, they're much further north than the present day -7 degree isotherm. So if we look at the pollen data and we plot the warmest period during the Holocene and that -7 isotherm, you can see the dots there of the corylus finds, they're well within that warming, that -7 isotherm. So it appears that the pollen data corresponds pretty well with the corylus. And here's a series of transient model simulations, and again, these are the warmest period during those transient simulations, and none of those simulations are able to create the winters that are warm enough to explain the corylus macrofossils, the northward distribution of those corylus macrofossils. Okay, so now I want to look at the same data, the pollen reconstructions as a time series, and this is just concentrating on Scandinavia, and it's really just I'm going to just lead you to an example to make you think a little bit about the importance of winter maybe, and how we can get possibly our kind of confused in understanding some of the mechanics of climate change. So here we have summer temperature reconstruction for Scandinavia, and it's another thing that I've also noticed that people kind of forget actually that Scandinavia used to be a lot lower. It used to be up to 180 meters lower at the beginning of the Holocene at the end, and that actually has a big climatic impact. We've actually corrected for that in this study, we actually calculated that, but that's an area average. So if you actually take some sites within Scandinavia, you will get up to 180 meters of altitudinal change, which makes it a lot warmer. And that's really important when you're doing data model comparisons, because models do not include that effect. So, as I said before, this is kind of very similar to that perceptual idea of climate change. This is the thermal maximum. This is the annual temperature, area average, again, gridded area average over Scandinavia annual temperature. So it's actually warmer than the summer temperature. And here's the winter temperature change over Scandinavia. And it's approximately over double what we're finding in summer. So winter is really important here. So I just wanted to show you a quick example. This paper came out last year by Zielhofer et al. And it's big data synthesis of, quite impressive data synthesis of Scandinavia and the Eastern Atlantic. And they basically, they mixed up summer and annual temperatures and basically kind of said, okay, well, they're all responding to summer in some way, so we'll just kind of put them together and see what happens. And they found two kind of principal components. One with about 45% explanation, one about 22% explanation. The interesting thing is also that they then, this kind of knee-jerk reaction, okay, it's summer insolation that's probably important here when we see that early Holocene to late Holocene trend. What's interesting is how closely they match the curves that I've just shown you. So whether it's winter or annual temperature on component 1, or it's the summer temperature curve for component 2. So I would say be careful conflating summer and annual temperatures. So in conclusion, it's quite an interesting problem. Was winter warming greater than summer warming? Actually, that's still an open question, and we still don't have the data to really disprove the fact that winter actually may be more important than summer. Seasons are important in attributing climate change mechanisms, whether it's insolation or atmospheric dynamics. And there's definitely there's a problem with models underestimating atmospheric dynamics, and we recognize that today as well. And just a quick mention of the project I have at the moment, working on extending this analysis to the whole of the Northern Hemisphere. Okay, thank you very much.
When I first saw the graphs, the maps rather, showing in your early graph, could you zip back to the very beginning of the pollen? So I thought you were going to say that the pollen, see the anomalies all in the Mediterranean and Eastern Mediterranean, circum-Mediterranean region. And I thought you were going to say this is because the pollen calibrations are wrong because the modern pollen in this part of the world is all messed up relative to the paleo record. And how do you account for that?
For the cooling, so there's a bit of controversy about whether pollen could reconstruct temperatures in the Mediterranean area. I would say two answers to that. One is we can discount modern analog. We're using these surface temperatures. If you have a modern analog technique method, then you're using surface pollen samples, which of course are from a modern day anthropogenically disturbed environment. If you compare the results with inverse modeling, for instance, so inverse modeling, we take a vegetation model and we run it backwards. So instead of putting in climate data, you put in vegetation information and it gives you the best guess climate from that. And we find actually they're exactly the same. And the inverse modeling also reconstructs cooler temperatures. Secondly, if you believe the models, so the models here have very warm summer temperatures. So you can discount all the pollen data, the climate reconstructions from the pollen data. If you feed that climate model data into a vegetation model, it will give you basically something virgin on desert, depending on the model. So it basically, it deforests the Mediterranean because summer's so hot in the model, and it's not, there's no precipitation. So it just becomes really, really arid. So, and there's absolutely no evidence of that occurring in the mid or early Holocene in the Mediterranean.
But isn't there vegetation in the PMIT? Isn't there a land surface model component where the vegetation is?
Yeah, I mean, we've done it. I can show you the results. Yeah, there's an aridity trend going back in time. So the mid Holocene is actually drier than today in the models. Okay. Yeah.